So I'm going to talk about some concept called the branch depth, which is new, so there will be lots of interesting problems. And the aim is to generalize tree depths in a graphs to different objects. So this is joint work with Matt DeVos and Simon Fraser and Oh Jung-kwon at Incheon National University. So if you have any questions during the talk, please feel free to ask me. Alright, so let me start with the definition of tree depths. So actually in the previous talk, Uyung already mentioned that he forbid some paths and then the path width is small, so tree width is small. But actually, if you forbid the path, the tree depth is small. You can have something more. So tree depth of graph G is a minimum K such that your graph G is a subgraph of closure of rooted tree of height K. So the rooted tree, so this is a example of rooted tree, and when you take by closure, I mean you connect two vertices if they are on the same path from the root to the leaf. And so the minimum such K is called the tree depth of graph G, and there have been some equivalent definitions like rank function, or vertex ranking number, height of elimination tree, blah blah blah. But this name comes from Yaring and Petrice's paper in 2006. So for example, the K23 is a graph, complete bipartite graph. If you compute the tree depth is 3, and because you can put one vertex here, I mean two vertices here, and then 3 on the other side as a leaf. So that's a tree depth. And if you look at the definition of tree depth, you use vertices and edges in various ways, right? Now, how do we generalize this notion to matroid, where you don't have a vertices, like you only have edges? Or how do we generalize this to analogous concept for rank width? So that's my question. So we want to have some unified framework that could extend the tree depths into other discrete structures where we are given some connectivity functions. Okay, so that's the aim. So that's why we want to think of some other thing. So here's another example where we did something similar. So tree width is a well-known concept in structural graph theory, where you want to describe graph as a tree-like structure. If you look at the definition of tree width, you still use also vertices and edges in a non-trivial way. So it's not easy to generalize to matroid, even though there is a paper which did it, who managed to do it. But instead of tree width, what people have done is to define branch width, where you only need the connectivity function. So branch width is defined for any connectivity function, where the connectivity function is symmetric submodular functions. So here are some examples of connectivity function that I've been interested. So this first one is the number of vertices hitting both sides of edge sets. So you partition the edge set into two sets, and you count how many vertices hit both sides. So that's one connectivity function. And if you use this connectivity function, then you get the definition of branch width of our graph. If you look at the partition of vertex set into two sets, and you compute the rank of the matrix, where the rows and columns, some row has rows are indexed by one side, the columns are indexed by the other side, and you compute the rank of this matrix, where the entry is 1 if two vertices are adjacent, 0 otherwise, and this defines some symmetric. It's symmetric automatically because transpose doesn't change the rank, and some modular by some magic, and so this is connectivity function. And if you use this connectivity function, you get the definition of rank width. And if you know the matroid by now, maybe you know matroid. And if you use matrix connectivity function, which is essentially the dimension of the intersection of the subspace spanned by left and right. And then you get the definition of branch width of matroid. So for any discrete structure, if you have a good connectivity function, you can plug in and use branch width. So can you do something similar for true depths? Okay, so that's what I want. So this is the definition of branch width, but perhaps I can just go through very quickly. So you want to have a tree whose internal nodes have degree 3. So this is one example where you have tree where internal nodes have degree 3, and leaves are labeled by the elements of your ground set of this connectivity function, such that whenever you look at an edge of the tree, the connectivity function of this set of elements induces a small value. So that's the branch width. So it's a minimum case such that such a thing exists. So can I make something similar for tree depths? But the reason, so here's one reason why branch width and tree width are tied. They are equivalent. So if one is bounded, then the other is bounded. Because for user graphs branch width, you have this inequality. So tree width of graph is then least to branch width minus 1 and 1.5 times branch width. So these two are tied. And they have been many studies. So so this is what I try to argue. So we want to have depth parameters, which is good for any discrete structures with connectivity functions. So that's so we want to introduce branch depths. And here's the definition. So right into the definition. So you have a finite set of elements E. And now I define decompositions. Decomposition is simply a pair of a tree T and some labeling sigma of the leaves of the tree. So this sigma is like same as the branch decomposition. So you label leaf of the vertices, leaf of the tree by the elements of the finite set. So here I describe it as a bijection from the elements set of elements E to the leaves of the T. Now this is decomposition, but then we want to measure the quality. So the width of the decomposition is the minimum K such that for every internal node, no matter how you partition these incident edges into two sets, the induced partition of the ground set E gives a small connective value. Okay, so this is this is for any subset of these edges, right? When you choose edges, you get like I chosen P1, P2, P4. Okay, you compute the connectivity function, and that function value is at most K. And this is true for any internal node and any selection of the incident edges, and this value is small. Then we say that width is at most K, and the minimum possible number K is called the width. But that's not the only quality. We also want to reduce the radius. So radius of the tree is another parameter. So we say something is a KR decomposition if the width is K, at most K, and the radius is at most R. Okay. Now, branch depth of some connectivity function is minimum K such that there exists a KK decomposition. Alright, so you want to find a tree with the labeling of the leaves so that no matter how we split the internal node into two, the connectivity function value is at most K and the radius is at most K. So that's the branch depth. Now the talk is not over. we should now argue why this notion is interesting. So first I want to show why branch depths of graphs is comparable to true depths of graphs. Okay, so that's the first step. Right, so branch depths of graph is simply you use this connectivity function. Whenever you have a partition of the edge set, you want to have a small number of vertices hitting both sides. I mean, that connectivity function is used in the definition of branch depths, then you have a branch depths of a graph. And here's an inequality. I won't show you the proof, but okay, so we prove that if graph has KR decomposition, so width K, width m most K, radius m most R, then true depth is bounded by a function of K and R. So that's one direction. And conversely, if true depth is K, then branch depth is m most K plus 1. So you can bound these two. So true depth, yeah, so you have this inequality, right? True depth is at most twice branch depth square minus branch depth plus 1. So that's one reason why these two concepts are tied. So if one is bounded, the other is bounded. No, no, we would like to have. Yeah. Okay. Now, what about the cut rank functions? Right? Cut rank functions was used to define rank width. So if you use the same connectivity function, we will get some depth parameter useful for rank width study. So, and there was actually a previous attempt to generalize tree depth to this concept, which was called the shrub-depth. And this was done by Robert and Peter, Yarik, Jan, and Petrus. And they had a conference paper a long time ago, but the journal version was published this year. And they defined something called shrub-depth. And we also show that a class of graphs is bounded shrub-depth if and only if they have a bounded rank depth. So maybe you want to see the definition of shrub-depth. And I heard that during this workshop where many people said, the definition of shrub-depth is ugly. And actually quite true, yeah, but it's recorded. All right. So we wrote it in this way. So KD shrubbery is a pair of rooted tree with n of labeling of the leaves, coloring of the leaves by K colors, such that every leaf is a distance d exactly d from the root, and the adjacency between the leaves, so the leaves are actually labeled by the vertices of your graph. Now you want to determine the edges of the original graph in terms of the distance in this tree T and the colors of these vertices. So as long as you look at the color of the leaves and the distance in a tree, you should be able to determine whether or not there is an edge from X to Y in G. So that's what's called the KD shrubbery. And then a class of graph has shrub depth D if and only, this is definition, if and only if D is a minimum number such that there is some maximum number of colors K, that every graph in your class has a KD shrubbery. So meaning that, let's say you have a class of graphs C. Now you want to say whether or not this class has bounded shrub depths or the shrub depth D, well, shrub depth and most D. Well, if you can find for any graph in your, there is some number, constant number K of colors. So that for any graph in your class, there is some tree of depth D, radius D. Yeah, depth D, such that any adjacency is completely determined by coloring of the leaves and the distance in the tree. So it's a bit weird parameter because if you take a single graph, you don't have a shrub-depth. Because if I have a single graph, I have a radius 1 tree and give different colors, everybody. And then adjacency is completely determined. So it's a bit weird, but we proved the following. So if you have a KD shrubbery, then you have KD decompositions. And if you have a KR decomposition, now this is scary part. You can find the AR shrubbery. So you keep same radius, but the number of colors you get is something like this. Okay, so 2 to the 2 to the yeah. We found the reason why we have this is that we want to find. So this is a bound related to the size of the universal graph. You want to find the smallest graph containing every k-vertex graph or something. Then there is some bound, and we use that to encode things. Okay, so that's what we have. But anyway, that just means that you have bounded shrub-depths. Right. Now, what about matroid? Well, we have seen matroid many times in this workshop. So, and rank function is the size of maximum independent set in the matroid. Now, we define branch depths of matroid to be the branch depth of the matroid connectivity function, which is defined like this: rank of set plus rank of complement minus rank of everything. Now, is it going to be the only concept good for matroid? Well, there may be some other alternatives, right? So we've been looking at these alternatives. So what could be the alternative? And here's another definition of true depth, which is recursive. So true depth of graph G is general if you don't have any vertex. And true depth is, if graph is disconnected, then true depth is the maximum of the true depth of the component. If graph is connected, then you delete one vertex and hope for the smallest number. And you add 1. So that's another way of defining tree depths. Now, for matroid, can you do something similar? We don't have a vertices, but why don't we just try the edges, edges, deletion or contraction. But then there are 3 possible definitions you can try. So one is the deletion depth. So let's say you only delete deletion depth. You only delete an element when matroid is connected. And you pay 1. Okay? And contraction depth, well, you contract, whenever you contract, you pay the price 1. And deletion contraction depth, you either delete or contract and you pay the price. Well, I mean, these are like sensible extension of these recursive definitions. And actually, this contraction deletion depth appeared in the on a paper by Ding and Oprowski and Oxley in 1995. They called it type, so type of matroid. So we want to compare these things and what we can say. And it turns out that we could draw this Venn diagram. And not only that, all the containment is proper. So we have an example where we can something here which is not bounded. Contraction, deletion depth, blah blah blah. And we also had this inequality, easy inequalities, right? Found, yeah, some of them are trivial, right? So these 2 are trivial, and this is well, you can do. Now, then you may ask, well, can we compare a branch depth of graph and the branch depth of cyclomatroid of the graph? There's a theorem for branch width. So whenever a graph is non-trivial, meaning, as long as you have some, if you exclude the really simple exceptions, then branch width of graph is equal to the branch width of cycle matroid of graph. You may have to add 1, depending on your choice of the connectivity function. Right. So how about that? Well, actually, for depth parameters, it's not true. So the path in a graph has a large tree depth, but if you take a cycle matroid, well, you get nothing, right? So you don't really have any independent. You don't have any circuits, so everything is independent, so you don't gain anything, right? So 1, 1, 1, 1. But if you have a cycle, you get something like this: log n contraction depth. So if you have a cycle, the contraction depth is big because the only way you reduce is contraction, but you can only reduce length by 1 and 1 and 1. Yeah, so somehow these things doesn't seem to be related, right? Tree depth is large, but the contraction depth is small. In the case of cycle, these two are related, right? One is large, the other is large. But then, we were able to say that whenever G is too connected, these two parameters are tight. So if the graph has tree depth T, then the contraction depth is big if and only if tree depth is big. But this is and then we could do further. If graph is 3 connected, then if tree depth is T, then contraction deletion depth and branch depths are all tied to each other. So this one is bounded and the other is bounded. Okay, so that's so if you raise the connectivity, then you can say a little bit more. So is that a good evidence? Well, I don't know. Now, how about the obstructions? Tree depth has a really easy obstruction. The graph has large tree depth if and only if it has a long path. We don't yet have any satisfactory answer for matroid. But we were able to prove that if you have large contraction depth, you have a long circuit. So circuit is a minimal independent set. And then by duality, if you have a large dilution depth, you have a long co-circuit. So that's some theorem. But we don't have a good theorem for contraction dilution depth. We made the conjectures that, well, if you have a large contraction dilution depth, you may contain one of these 4 matroid, but even if you contain them, it doesn't guarantee that the contraction deletion depth is big. So, because this parameter is not minor monotone. So, it would be better if we have some better description of obstructions. And this has been verified for cycle matroid. So if you have a cycle matroid whose contraction deletion depth is big, then you contain one of these 3 as a minor. So this Fn is not this is Fn in the cycle. It's a cycle, replace each edge by parallel edges with N. And we also tried to find obstruction for large branch depths, and we thought that maybe a fan and the uniform matroid could be obstruction. We don't have a proof. So that's what we have for matroid. Oh, by the way, I'm not the first one who tried to think of the depth parameters for matroid. Actually, Cardos, Dankral, and Ma, they had a conference paper in 2017 where they defined branch depths of matroid. The same name. And it's actually equivalent to the, I think it's equivalent to the contraction depths in some inequality. So to distinguish from my branch depths, I wrote KKLM depths, and yeah, so we were able to show that this is same as contraction depths. Alright, and then well-coordinated ordering. So there is a theorem for graphs that proves that graphs of bounded true depths are well-coordinated ordered by subgraphs. So in 1985, there's a survey paper by Robertson-Simmer, and there's just mentioned this without proof, because this was easy, and this is, when I was a graduate student, this was a homework problem. And then Guru-Ding extended it, that graphs of bounded tree depths are well-coordinated ordered by induced subgraph relations. And we try to generalize the, find the analog for matroid. And now, well, what we think of, so if you look at the cycles, C3, C4, C5, subgraph is like the leading edges, but cycles will never be a restriction of another. So by restriction, I mean you delete elements, delete edges. So they form an infinite chain. So in order to say that they are well-coordinated by subgraph relations, no, not subgraph, in the matroid restrictions, we want to say that, well, we cannot have an infinite anti-chain, so we cannot have a long circuit. So it's better to forbid the long circuit. Then this construction depth is small. And so that's what but we also have to make sure that this matrix is representative over a fixed finite field. If it's representative over infinite field, then it's not well-coordinated. There's some example in old paper. So the theorem we had is that if you have a finite field, F, then F representable matrix of bounded contraction depth is well-coordinated by these restrictions. So you can delete elements and you get smaller one. So we have this characterization. Some infinite set of matroid is well-coordinated by some infinite set of F representable matroid is well-coordinated by restrictions if and only if you don't contain long circuit, and if and only if contraction depth is small. Right. So here's a summary. Now it's time for lunch. Exactly. Right. So we define the branch depths, and as an analog of tree depths. And if you use different connectivity function, you get different definitions for different objects. So if you use cut rank, you have a rank depth. If you use matroid connectivity, you get the branch depths of matroid. If you use vertex connectivity, we get the definition of branch depths of graph. And then these two cases, we found the connection to existing concepts. For matroid case, we found the many layers of different depth parameters, and they had some containment relations, and we found that all of them are proper containment. And the well-coordinated ordering result for tree depths was generalizable to only this case. So that's the summary. So one open problem for this audience is that can you find the KK decomposition in FPT algorithm by an FPT algorithm? If it exists, I don't know whether we can. The existence of such a thing can be done. Yeah. So this branch depths. If you work on rank depths, things can be encoded. They are closed on the vertex minors and it's well-coordinated ordering, so you can find there exists final list of obstructions. You use monad second order logic to do it, and they will have a bounded rank width or bounded branch width, so you can do all these things. But finding one such decomposition seems different. Okay, so that's it. Thank you for your attention. Okay.